able to know the 5-number summary quickly and easily. As always, least to greatest. Laura, 1,000 points right there. And let's do this.
I found him. What's he doing? I don't know.
The 5-number summary is the following values.
He's talking to someone.
From least to greatest, min, Q1, median, Q3, and the max. Nice answers. If you put the 5-number summary in the chat, you get 1,000 points. Keep these answers coming.
What is it? What happened?
Hey everyone, how are we doing? It is time for office hours. I'm going to set up some stuff online. Hair's getting a little longer again. It's all right. I like it. Here we are setting up our class, Stat 201. Let's take a look. Data analytics number 7. Going to the assignment. Might do some notes on it or how to do it. Probably add it in. I don't think it has the extra things, the extra stuff. Let's see right here. I think it has both confidence intervals. It does. How are people doing? See if I don't get copyright claimed on this song here. And let's go to the playlist. Go to visualization assignments. Visualization assignments right here. And let's go to confidence intervals for the true proportion. And put it in. Okay. How to make confidence intervals for the true proportion. How to make confidence intervals for the true mean. And so, video help with interpretation. Video help with interpretation. There, and do this. Drop that. And then right here. And right here. What? Oh, I didn't copy paste it right. Totally didn't. There we go. Got that. Update assignments. Save. There we go. Saved and ready to go. Okay, so I got that ready to go. Let's see. What do we got coming up right now? Just gotta look at the calendar. Got April 22nd, big day coming up right here. We've already done a lot of these assignments. So let's see if anyone's in the chat or messages. Got save the date emails. A lot of stuff coming in. Yeah, there we go. We're doing that. Okay. Good news. So much good news. There we go. Be doing more events. Let's do a little map here. When is the data analytics due? Data analytics is due on the 25th. So no one's started yet. We'll do a little more. Maybe some chapter 14. Okay. I'll have to mention tomorrow. I'll be like, do the homework. Got a lot of videos doing the homework. Song's still playing. Got to the homework. Get it done. Okay. And I'm still tired. I need Red Bull. I shouldn't drink Red Bull, but I want it. I got addicted to it. Caffeine addiction is a real thing. And I have it. So confidence intervals for the sample mean. Let's do some of the homework assignments. Okay. So let's get the notes up. Where is it? Here we are. And there we go. Let's do it. Okay, so these are some pretty easy multiple choices to start. Let's start off with them and see how many we can get and how easily we can do them. So this is at the 5:23 mark, or 24. So we got Stat 201, Chapter 14. confidence intervals or quiz, easy multiple choice. We're going to knock out the easy multiple choice right here. Okay. So this one talks about, we have a sample size of 15. What number of degrees of freedom should we use? And it says we're making the 95% confidence interval for the mean. That's actually very important. It hasn't been properly illustrated yet, but let's go here and type review 3. And Mubot's going to drop the review notes in the chat. He should. I think he's awake right now. He is awake. He's in the chat. I think he is. We had a period of time when Mubot wouldn't work, but he's dropping the link right there. Mubot is awake, and there's the link in the chat. So we're going to go over here to review 3. Now, it says we're making the confidence interval for the mean. So if you go to the formula sheet right here, what you'll see is when you make a confidence interval for the mean, you're down here, confidence interval for the mean, and it says degrees of freedom are n-1. So this is the important part you should be noticing, is we're doing a confidence interval for the mean. We'll highlight that. We're doing confidence interval, and then degrees of freedom, which tell us the shape of the distribution. We can look at that also. We can go to stat distributions, and we should know that the t has a metric called degrees of freedom. When degrees of freedom are low, it's more flattened out, and when they get higher, it becomes more like the normal. So higher degrees of freedom means more normal, usually equating to a higher sample size, especially for the one sample t. And so the answer is very clearly, if there's 15 sample size, degrees of freedom are 14, n-1. So once again, understand the concepts behind these. Degrees of freedom tell you the shape of the curve you're using. Good stuff right there. Do we have any other quick ones? Here's another quick multiple choice. Which of the following is true about the family of t distributions? So it's called a family of distributions because there's not one t distribution. There is only one normal. So if we go back here to statdistributions.com, really good site right there, stat distributions. On statdistributions.com, you can click the normal curve, and it's not a family of distributions. There's only one normal curve. So when you have the normal curve, it's not a family. Family means like a whole bunch of distributions. And when you go to the t or any of these others, like the chi-squared, which we're not using right now, there's different chi-squareds, and they have different shapes. So the f also is the ratio of 2 chi-squareds, so it can have way different shapes. The t, which is the one we're using right now, has a shape depending on the degrees of freedom. As you get higher degrees of freedom, it becomes more normal. And so let's look at what they ask us to describe about it. The t is unimodal and symmetric. Well, we can just look at the t over here. Is it unimodal symmetric? You bet it is. It looks like the normal, basically. T's distributions have fatter tails and narrower centers than the normal model. That is true, and especially at lower degrees of freedom. So if we go over here and go to really low degrees of freedom, they are much fatter and narrower towards the center, and you can really see it right there. That's really a low t degrees of freedom t. As the degrees of freedom increase, the t approaches the normal. That's exactly what we saw right there. So we did amazing on that. We did such a good job. So let's look at a few more right here, and we'll switch it up. These are some of my favorites, actually. Let me get the screen oriented right here. We'll get the screen all oriented up for this. Got so many things going. Okay, so we need to get, for this, we're going to go here to Adam Spanbauer's site. I know you can't see the screen right now. But we are going to get it organized nice and perfect. Okay. Check this out. Okay. So this is the t distribution right here. And we're actually going to mark this one in the notes so people can find it later, because a lot of people ask about this one. And so this will be at the 9:13 mark. What's up? Research. Yeah, let's do that one. We'll do it right after this. Yeah. So do you know how to do this one here? Thank you so much, Sophia. We got that one next. We'll do this one pretty quickly. We'll be doing yours in just a second. Do you know how to do this one right here? How do we have to have the t applet up. And so then how do we do this one right here? It says make a 90% confidence interval with degrees of freedom equal 3. It's a tricky one to guess. You have to put between, you have to be using the t, and then you have to put the degrees of freedom, and then you have to put in 90. And there's the answer. So the next one just follows. The next one says, what is the critical value for a t with 99% confidence? This one we can guess. It's probably about 2.59 or so. We'll check the answer right there. Oh, it's 2.58. It really approached that. Ooh, what did I do wrong? Dun, dun, dun. What did I do wrong? I feel like I must have, with 3 degrees of freedom, 2.5758. Ooh, it's higher. It's like 61. There we go. I can't guess them that easily. All you have to do is put in the number and put this in, and there it is. So now I got close enough. I should have guessed a little bit higher. Put in the degrees of freedom that it tells you to. Put in the percent confidence, which will shade the middle area on the curve, and make sure you've clicked middle, and make sure you're using the t distribution. So let's do Sophia's question. How are you doing today, Sophia? We'll throw you some points right here. We'll do the waist size one. So waist size question might be, I bet it's this one. Is it? I've done these too much, Sophia. I've done this question so many times. So many times. We planned this. Okay. I'm going to write the note on it, and then we'll do it. Okay, got that there. And researchers measured the waist. I like that people, they're the same order for me since I can see every question, but sometimes people say, do question number 5, and I'm like, I don't know which one it is because your 5 is different than my 5. Okay. This one deals with what the mean and the standard deviation should be for a distribution as for a sample size. So here's the thing. If you collect 2 men, what would you expect their average waist size to be? If you collected 2 men and the average man has a waist size of 38.383 or something like that. So if you collected 2 men, that was the instructions for the project or the previous project. If you collected 2 men and the average waist size of the men was this, what would you expect the mean of 2 men to be? Well, it's just like I'd expect them both to be around that, so I'd expect the mean to be what? This is kind of a review, but it goes into this chapter a little bit. It's mu y bar equals mu. And so since this is mu, it's asking about what do we expect this quantity here to be? And the answer is simply this quantity, which is this quantity. So the answer for all of those is 36.383. Now over here, the standard deviation is sigma over square root of n. So this is sigma, which is the true standard deviation, and then the sample sizes increase from 2, 5, 10, and 20 respectively. So all we do is take 4.189 and divide by square root of 2, and we just go to the higher values. Does that make sense? We're just going to do 4.189 divided by square root of 2, 4.189 divided by square root of 5, 4.189 divided by square root of 10, 4.189 divided by square root of 20. So you just plug in the values of the sample size. That's just n right there. So it's n is 2 for the first. You'll increase sample size, but plug in your first sample size of 2 and go through the vector or the values in sample size. And this is the sigma. The sigma will not change. It's the same sigma, but change the values by which we go up sample sizes. Put them all in and ascribe those values into here. This value solves out to SDY bar, the standard deviation of the sample mean. So that's the SDY bar, and that is the quantity we want over here. So that is the value we'll solve. And let's see. We'll get this solved. Drop another one in the chat. This one will be done in just a moment right here. Once you understand the concepts, they get really easy because it's finding out what to put in them that's the problem. It's like, well, what do we have to do? How do we solve it? And then we're just going to take and do 4 or square root of 2, which is 1.414, I think. Yep. And then 4.189 divided by square root of 2. Drop this in, delete down decimals. And then square root of 5 is like 2.3. No, 2.2. And 4.189 divided by 4.189. And drop this in, make sure to round. And then square root of 10 is going to be like 3.2. Close, yeah, it's rounded. And then 4.189 divided by that. There's this. And that's going to round up. And it says to 3 decimals, good. And then square root of 20 is going to be like 4.6. 4.52. Yeah, close enough. 4.4. And 4.5 rounded. And we take... It's going to be a little less than 1. I always tell myself what it's going to be, so if my guess is way off, then I'm like that. 4, I didn't hit enter. Because if my guess is way off from what it actually is, either I'm bad at guessing or I entered it in improperly. So we want to make sure we take guesses because it helps us see if we got it right. So here are the actual or there's the distributions, and here's the theoretical values of very close to it. 1.8, very close. 1.3, very close. 0.9, and all these are very close also. Simulations do mimic reality, and if you notice right here, it's only got a little bit of right skew, so it's normal around 5 or 10. It's normal pretty quickly because it's not very heavily skewed, which is the large enough n condition. So theoretical values are reasonably close. The theoretical standard deviations are reasonably close. They're not exactly, because these are the theoretical values These are the simulated values. Simulated values right here, theoretical values, they're pretty darn close. And use a sample size of, this is where it gets tricky. So we're basically saying, when does it become normal? That is tricky. What about the shape of the distribution of waist sizes explains your choice? Well, originally it wasn't very heavily skewed. The distribution is very unimodal and symmetric, so the sample size, so the sampling distribution of the mean is close to normal for even small sample sizes. It's either 5 or 10. Really? Is it 10? I didn't lose that many points for the 10, did I? So that was right. I made a mistake elsewhere. Okay, did I divide the wrong numbers? The mean and standard deviation. I did something way wrong. What did I do? The theoretical values are reason. I must have messed up these values up here. Round to 3 decimal places. 36. Sophia, do you see it? I would give a student their points back for this. Do you see it? See if you see it. There's 4 wrong answers. I'm like, come on, man. Come on. I can't type. So the only issue was I put the number wrong. I put a 9 instead of an 8. That was it. I just typed a number wrong. Yeah, that was it. It was just a typo. It's 36.383 and I did 36.393. I just typoed it. It's usually what it is. Just can't read numbers. I looked and thought I said a 9. Everything else was correct. It's all theoretically correct. So this is using, we've got it all mapped out here on how we solved it. Talking about the sample mean, or excuse me, expected sample mean is equal to the mean, and the sample standard deviation of the mean is equal to this. So we've listed it all out, and the simulations then show reality. Want other questions? I don't love that question's there. It's a bit of a review question. This is the exact same question, just with different data. Literally the same question. This one gets people stuck. We haven't done the chip challenge one in a while, so we probably should do it. People get stuck on how to do this one because it's better with jump. So I could do the chip challenge one. Just a lot of people say, how in the world? It's like, use jump. Using jump on this one makes it way easy. It's super easy. If you don't use jump, it's pretty tough. It's more work. Okay, and drop another question in if you want. So you notice we get 12 data points right here on the chip challenge. People went in and counted how many chips were in a chocolate chip bag. 1882, you got it. We'll do that next. Ooh, that one like has so many decimals on it. That one's annoying and it requires a little math trick, but we got that one next. So this one right here, we're going to copy the data, copy to the clipboard and hit copy. Notice there's no column name at the top. So when we go over to jump, we're going to have to make sure when we go to file, new, data table, we just edit, paste. Do not paste with column names. Notice there's no column name. If you paste it with column names, you get this, and that is going to cause problems because your first value went up here, and that's not a row anymore of values. You only have 11 observations, or 13. There was 14 originally. I said 12, but you lose an observation. Don't do that. Just make sure to not paste with column names. So we're going to cancel. I don't want to save it. Okay, so now that we've got it properly pasted, we're going to go to Analyze Distribution, and we're going to double-click column 1. And then we're going to paste it in. Now, it doesn't look exactly the same, but we're going to fix it up. We're going to hit the top red arrow and go to Stack. We're going to double-click the axis right here, and we're going to go between 900 to 1600 in units of 100. So double-click. Then we're going to say 900 to 1600 by units of 100, no minor ticks. And that should look right now. There we go. That looks about right. We're going to hit OK. It's down here at the bottom. And there we go. So that's the shape of our distribution. Looks just like this one right here now. So this is the answer. Check your conditions. The conditions are condition 1, random. Condition 2, less than 10% of the population sampled. This is probably a random sample of chips. It's probably less than 10% of all chip bags there are. And they only want the randomness condition met. The data is a random sample, so they can be assumed to be independent of each other, which we want them to be random independent samples. Good for us. And condition 3, large enough n, which they're not checking, are they? They're kind of checking to here. Evaluate the histogram. The histogram is roughly unimodal and symmetric, so one can assume, this one sometimes gets me, roughly unimodal and symmetric, with no outliers, so one can assume that it follows the normal. I really hate the way, so it's not bimodal, we're just down to these two right here. These are the only two plausible answers. The histogram is roughly unimodal and symmetric, so one can assume the data comes from a population that follows a student T model. With no outliers, so one can assume that data comes from a population that follows a normal. I hate the way they phrase this. If I'm going to get something wrong, good thing you're watching this, it's going to be this one, and I triple guess myself every semester when I get to this one. The 95% confidence rule is a joke with JMP. We could solve it by hand, solving the T and everything, but we already have the answer over here. Boom. And it would come from a normal population. We'd model the sample, we'd model the confidence interval with a T. The population is probably normal. I think that's it. We're modeling, yeah, if it's mad at me, the population is probably normal. So we can assume the population is mostly normal because the histogram looks mostly normal. The population wouldn't follow a T. We'd make a confidence interval with the T distribution. All we're going to do is put in the numbers. I'm going to put it over here so I can see it on the other screen. So I'm just typing in the lower value in the upper. It's to 1 decimal, so 1178.3. And then the upper value is 1291.1. And then we'd go right here. I am 95% confident that the true mean chips in a bag is contained in the interval 1178.3 to 1291.1. But this is not about every single bag. It could be the case that some bags have more or less. So because the interval is entirely above 1,000, the mean number of chips per bags is likely more than 1,000. However, the normal model predicts that a small amount of individual bags will have fewer than 1,000 chips. Boom. Man, I really double thought that one right there, and I got it. I was like, the population would be more. Ayo, what's up, River? Good to see you here. We're going to do a speed of light problem. I think is this one. You ready? Oh, I meant to click that one. Let's pulse rate. Happy birthday! Happy birthday! Let's throw 5,000 points. I like that. Happy birthday. Hope you're doing something fun for your birthday. Happy birthday. What are you doing? Are you gonna get some dinner? Enjoy some time. I hope you're having some fun for your birthday. I had friends over. Nice. Yeah, it's probably like, wait. Is it early in the morning for you? Is it like 1 a.m.? What time is it? Oh, I've heard that game is good. I should get that for my wife and I. Here we go. Oh, is it night? Damn. Man, you're on. Because you're back in time, I think. Wait. Yeah, you're back in time. Because we're forward in time. Forward and back and forward and back and forward and back and forward and back and forward and back. Let's see. Speed of light. Is it Michelin measured the speed of light? No. Are you so far back in time? I'm back in time. Oh, you're right. You're forward in time. It's nighttime on the 21st where you're at. How does that? I don't even understand it. I don't know. Oh, is it the Grand Meridian where time changes? I don't understand the world. I've lived in America too long. The last time I left this country was in 1996. Like almost 30 years ago. Is that what it is? That's the Central UTC plus 2. Gosh, we're just like Eastern, Pacific, Mountain, and Central time here in America. Last time I left America was almost 30 years ago, like when my students weren't born. I went to Jamaica. It was the church I was with. It was like, yeah, they were like, let's go. We built stuff and did stuff. I got burned. I got pictures of it. Should find those pictures. I had long hair to my shoulders. But yeah. Okay, you ready? We'll knock out this problem now with some more fun. You ready? And happy birthday. Let's throw another 5,000 points. No. It's I have my view. Here we go. We went to Jamaica. It was a thing. But yeah. Okay, here we go. What time is it after this? You ready? Okay, 24. Here we go. Okay. In 1882, they measured the speed of light. Now, this is where this question gets weird. Because they want us to subtract 299,000 from all of these values, which I really, they should have just given us the values. But they changed the values that there'd be, like this first value right here, see here, this is where this question is like, what are they telling us? This first value is 299,756. Why don't we just say the speed of light is 300 miles per hour? Why don't we just do that? Like, let me Google it. What is the speed of light? What is the speed of light? Yeah, literally it's showing this right here. And it's actually outside the upper bound. But that's even, does it have the decimal? Oh, what are they doing putting decimals on that? Should be 300 meters per second. Oh, are they doing it in, they're doing it in kilometers. Kilometers. That's basically it, right? Meters per second. I said miles, but it's meters. And that would actually change it vastly. So it's in Jesus, I'm just cracking myself up today. This should just be 300 million meters per second, right? Or 300 million meters per second. Yeah, so this is in kilometers. So it's just times it by 1,000. So they're doing it in kilometers. And I don't like that they describe it this way, which just makes it weird. And so what they want us to do is they want us to make a 95% confidence interval for the true speed of light. It's because there's measurement error in it. And a lot of times people say we only know the one-way speed of light because go talk to physics, because they'll tell you why or whatever on that, because that's something I don't say. I just do the math for this. So what do we have to do right here? To build a confidence interval for the mean, we have to do the following. Let's take a look at the math. And why is this acting? Oh, it's still on the other screen. So to build a confidence interval for the mean, we have to do the following. Y bar plus or minus T star with n minus 1 degrees of freedom. And with this, we do S over square root of n. So this really boils down to knowing notation. And let's grab the work. Okay. So Didi or Sophia, I need any help with any of the parts of this. So do you see any of the notation in this problem? Any of the notation to solve it? We're going to color code it and see what we can get. Do you see any of the notation? Any notation in this problem? Like there's numbers. The numbers are going to help us. So any of the notation. Be like, oh, wait. See if you can get any. If you can start solving these problems, that's where you want to be at for the test. So you want to figure out, yep, n is 23. And so that'll go right there. It's going to get degrees of freedom. Standard deviation is going to go right there. And n is going to go right here. Whoops, wrong thing. And we're almost there. We're doing so well. We are flying along. And guess I'll grab this one for you. The sample mean. And now we just have to get what? There's a few other things we have to get. We need to find this quantity right here known as df. So the df, the degrees of freedom, is 22. And now we're going to go and get what? What is the only thing we're missing? The quantity of df, which is degrees of freedom, is 22 degrees of freedom. We now need to go find what? Yep, a lot of times people do that. It's just for some reason our book and everything. It's not a problem if you call it x bar or y bar. It's just the mean of variable x. And so you can call it either one of those. A lot of formulas will call it x. We call it y because we want to call it the variable of interest, but tomato.
It doesn't matter.
Yeah, T star, you got it. So the T star is relative to how confident we are. So we'll use the Spanbauer one. Let me go do that. So this one's really good. I do like this one. I didn't put the full thing. MuBot's going to send us to the T-applet right here, and we are going to build, I think it was a 90%? What percent confidence do we want? 90%. So the star means relative to a certain confidence level. And so we're going to go to the Spanbauer applet. We're going to put in 90% confident. And what is the only error I made right now? What is the only error I've made? I've made one error. See if you can find it. The degrees of freedom are 22, because 23 minus 20 minus 1. 90% confident. What is the one error I've made? Don't worry if you don't know it, but there's one error on the screen. To get a confidence interval between, you got it, infinity. That's worth 5,000 points for error. 1.72. Mulot only listens to me for some reason. He only likes me. So 1.72. So T star for the 90% confidence with DF equals 22 equals 1.64, was it? I forgot what it was already. 1.72, I think. That's wrong. 1.72. There it is. And now, this thing pops up all the time. Those things. Brian. It's so weird. I think I have it. I think I could make it so he'd respond to other people. 756.215 plus or minus 1.72. And then 107.116 over, and then 23, and then needs to be square root of n. So I usually solve the margin of error first. So when we solve the margin of error, we go right here. And Sophia, drop another one in the chat. Give another question. There's that. There's that. And that is the margin of error, 38.42. Did it say how many decimals? 38.42. It's going to want one more decimal, isn't it? It's going to want one more. 1.6 or 1.7. It's ridiculous. 756.215. That's a 2. And so now we just simply add and subtract. Now this is where I really get mad at this problem. I'll show you why. 756.215 plus this. 794,631. We're just adding and subtracting the margin of error. Software analysis, you got it. And then we're going to subtract. There's the mean. There's the margin of error, or there's the lower. 717,798. There. Okay, I'm going to bring this over to the other screen. So many things. Let me screenshot it. Screenshot. There's the answer. And go back over here. And we can drop in the interval. The interval is right there. I'm going to bring it to their screen so I can see it. And it wants to 2 decimals. Of course it does. You have to enter in 299. You have to add back on the numbers that they subtracted off. I hate that they do that, but they want you to do it. Unless I've made an error, it's always possible. That's rounded up. And then 299. And then the lower bound. Oh, that's the lower. Yeah, that's the lower. And the upper bound is 794.63. I think they were like, ooh, people will love that we're calculating the speed of light. I am 95% confident that the true speed of light is contained in the true mean speed of light is contained in the interval blank to blank. Which of those sounds right? A, B, C, or D? I am 90% confident that the true mean speed of light is contained in the interval. Which of those sounds right? A, B, C, or D? I am. Yeah, it's not too bad. I am 90% confident that the true mean speed of light is contained in the interval blank to blank. Those numbers. Which of those sounds correct? Because heavy like light, is it? Oh, yeah, light. I get it. I didn't get it at first. I like it. Any guesses? A, B, C, or D? I am 90% confident that the true mean speed of light is contained in the interval blank to blank. Which of these sounds right? A, B, C, or D? And on the test, you have to write it out. So that's where people get stuck. A or D? And so in good answers, it is D. So it is D because we're trying to figure out the true mean speed of light. It's not for the samples because when you take a sample, you make estimates about the truth. We know what the sample is. We don't know what the truth is. Because we can say like, well, from our sample, we saw a mean of this. Now, we're not estimating what the truth is for the sample. We're estimating the truth for what speed of light is in the overall fashion. And what assumptions did you have to make? Here we go. The measurements are independent. Yep, random independent. The data follow a distribution that's normal and reasonably symmetric. Sure. The measurements arise from a random sample of suitably randomized experiment. I hate the way they're phrasing these. Would not be a uniform distribution. The sample is drawn from a large population. No. So we got here random samples. They're calling independence too. It's basically random. And unimodal symmetric. What did we do? Do they not want us to add back on these numbers? What did we do? I did the interval wrong. I can't math today. What did we do on our numbers? Well, Brian can't math today. It's too hot outside. Okay, let's look at the math we did, and let's try to figure out what we did wrong. Okay, so we are building a 90% confidence interval. And we have to have made an error here somewhere. It's a math error that caught us. We got everything else right, it looks like. And so let's look at our math. 23. I can't math a lot of days, it seems. 107.116 divided by that times 1.72. That's 38.42. 38.42. Is it a rounding thing? 38.42. There's that. 756.22. 756.22. No, I don't do that. 756.22 minus 717.8. I feel there's a math error here somewhere. So this is the mean. That's the standard deviation. That's the sample size. That's the t-statistic. 756.2. And then we add back on the value right there, rounded 2 decimals. Try 215 instead of 22. Which thing? Let me see again. Try 215 instead of 22. Oh, 215. Yeah, let's see right. It might be just, if it's off by the tiniest of decimals, I'm gonna be so mad. Yeah, I could be the rounding on the decimals. Okay, let's try this again. Let's work out all our math, carry all the decimals. Because it's seriously, if I was off by the tiniest of decimals, that is ridiculous. Okay, so that's every decimal carried. Everything's right. And we have to divide by square root of 23. So you got to do square root of 23 first. And then you go 07.116 divided by that. There's this. So this, and then we times this by, no way. Is it the t-statistic we didn't carry enough decimals on? 717. This might literally be it. If so, this is wacky. And I'm very like, you gotta be kidding me. It might literally be that this should be that. That might have caused a tiny decimal error because we didn't carry enough decimals on the t. I should have thought of that. So this is the standard error currently. This is quantity known as the standard error, s over square root of n right there. So that is this quantity right there, s over square root of n, is solved in the calculator. Now we're timesing by the t, which gives the margin of error. So the margin of error is 38.352. We're going to carry every decimal. And look, we're already seeing a little difference over here, 38.352. I think that's going to create the tiniest of fractions of errors, 38.352. And we should have looked at the decimal differences, but now we're going to change. It's only going to be the decimals at the end that are going to change. And with this, we take this number with all of its beautiful decimals, and that's going to be 57. And then we're going to subtract the mean minus this. This brings us back to the mean. And then we're taking 756.217, which is the mean, minus this. And we get 0.86, rounded to 2 decimals. And we're going to screenshot and take a picture. And we're going to say, please work. Please work. And I think we have everything else correct. I hope so. Was there only 2 other blanks? If there's only 2 other blanks, we do have it correct. Yep, looks like we do. Okay, so notice this value right here. Apparently, we just need to change it to this. If that's how much we were off by, that is ridiculous. Because I don't see any other errors in my math. I think that's right now. It's because we didn't do the t-statistic to 4 decimals. I'd give that one back. I would give that back. It was literally because we didn't do the T to 4 decimals, which is, people do it to 2 decimal a lot of times, or computer software does it for you. Like when we do it inside a jump right here, which we did for the Nabisco problem, jump will carry out the T to whatever decimals. It'll just use all decimals. Like it'll be like 20 decimals. We have had that. Yeah, I know, right? I couldn't see. Man, it's just like, it literally to 4 decimals with a T. I was like, I don't see my math here. I don't see it. So good to see everyone in the chat. People are cracking me up right there. Yeah, it was literally a decimal. Are you in UT, Kata? Are you? Let's try to see what the picture is. Is it a UT test or is it like another? Brando, we got it. How many people are here? We throw another 5,000 points. We got everyone here. Cool. Yeah. No, sorry about that. Sorry that. Is it a Statue 1 test you had that up in there? You're like, man, I was in a biology class and we didn't have we had to carry the T out to 50,000 decimals. 4 people are watching. Woo! Carry your T out to 1 billion decimals. Right here and just be like, there you go. All the decimals. Plug that into the calculator. What's really great if you're using software like R, use R right here. Let me bring R over the main screen. You can actually get the T really well with R by going to, I believe it's PT. I always get it. It's either QT or PT. You can go QT. Is it QT? And let's go right here. There we go. There's the T. And then you can go options. No. Options, decimals. Option? Options? Decimals? That works. Am I going mad? That was options. I don't know how to change anything. If there's questions, please ask. Changing decimal reporting in R. Those options. Options digits equals 4. There it is. Digits. There we go. There you go. So you can get all the values reported to you. You might be wondering why I'm putting 95. It's because you have to go to the 95th percentile. So when you make a 90% confidence interval, this boundary only has 5% above it because it has 10% on the total outside. So you could, like I'm doing right here, go to the 95th percentile and get that same value that we see right there. So you have to do it a little bit differently. But yeah, it probably would have been fine if we did 3. If you get something off by that, just let me know. If there's a tiny error, I'm going to close a few things on the screen right here. Closing all the background windows. Closing all the background windows. What other questions? I feel like I should drink a Red Bull. Or I shouldn't. I drink too much Red Bull. Too much Red Bull. What questions are there? So good to see everyone here. Sure, site. Oh, man. I wonder what ChatGPT can do for us today. Maybe we'll end with some ChatGPT. Okay. Let's see right here. I'm going to close my window. Let's see here. Design a really cool game inside of R with Shiny. This game needs to have left, right, up, down controls for someone to use and must be very fun. Base it off the best Shiny R games there are. This needs to wow someone with really up-to-date packages. The code needs to be... Any pointers on the staff project? Yeah, we should do that another stream. And because the project is due when? It's coming up. When is the project due? What date is the project due? I've got everything over here. I'm gonna see if this can do it. The project. We could do that tomorrow. Oh my gosh, there's a billion things to say project on here. The project is due on May 2nd, a week from Friday. So, and April 30th early. So here's the project right here. I'm going to do some big help sessions on it. So like the big help, like with Nickelodeon. But we'll do some big. We could start it tomorrow and talk over it. How's that sound? Are people going to be here tomorrow? Because we're finishing up today's office hours. Who's going to be here tomorrow? We'll be. Is it earlier tomorrow? We're here early tomorrow at like 11 Eastern Standard Time. So swing by right after class. Is it 11? Is it 11, Brando? It is, right? Because we finished class. We finished class and then we go right into it. So because it started class at 9:40 or so. Then we go. I might just do office hours right after. Let's do it tomorrow. Needs to make an app that uses the best packages. Please make it look beautiful using shiny widgets or better things. Okay, let's see what we got. You ready for this? Okay, what do we get? Shiny game, arrow controls. The point of the game is not to control arrows. He doesn't understand. Press start 2-player. Why are we having 2-player game? Okay. Let's see what this does. Okay. What are we doing? Okay, it's actually making controls. Ooh, it's JavaScript right here. Running JavaScript. Okay, I have no idea what this is going to do. It doesn't understand the point of a game, I don't think, but let's find out. What did we get? Okay. It's gonna load. Retro Pixel Runner. What? It actually works. What in the world? Look at that. What's the button do at the bottom? Oh, it's got the controls. What? We just made this in seconds. Oh, wait. You ready? Let's say this. Okay, let's go back here. Awesome. It works. Now I want for letters to start coming in and you have to dodge them. If a letter comes in, you get a point, but if the letter hits you, you get a game over and it ends on a ending screen. The letters should start out slow, but then speed up over 5 minutes. Okay. Let's see what we got right here. Yeah, it's just what you can do with ChatGPT is insane. You just have to be able to think it. So let's see if it does it, because that wasn't really a game, but it made a movable pixel, which is still pretty cool. It'd take me like a week to do that. If someone's like, code a pixel that can move up and down, I'd be like, okay. If you look, it's kind of the same thing. If someone presses this, do this. And isolate, like, finds out the keyboard you do. If game over, return. Okay. Okay. It's not that much extra code so far. And then it's moving the other letters. That's good. Check for collision. Okay, so it's going to see if you're in the same spot. If collide, then game over is true. So then it changes that to game over. And this might work. This might work. Looks theoretically accurate. We're getting the same old thing. What do you feel? Oh, wait. Oh. No. It broke. Did I get hit by a letter? Yeah. Okay, last try. For numeric objects. Okay, we'll say. So close, ChatGPT. So close, but I get the following error. Please make it work. Invalid format. %D use %F, %E for numeric objects. Let's go through its editing. This is our last try here. Make our little game. I love what you can do with ChatGPT. I run out of my ChatGPT like every day. I'm just using basic ChatGPT. So what did it update? Looks like there's an issue with how the letters are rendered using Render UI. Yeah, so it can't render the attack letters. And it just crashed. Yeah, that just crashed. It already worked with a red pixel, so let's just not use letters. Let's just use other pixels attacking you. Like, you just have to think, like, you're like, okay, why did it work? Well, it worked before with pixels, so why did I ask you to use letters? I don't know, I'm gonna call it like letter attack or something. So this is our last try right here. Oh man, we almost got this. If this works, we'll have, there's the enemy's data, the position of the enemy data, looking at the collision. And better reading code. When you encounter the error. Oh, we're still running the app. It just crashed again. What did it crash on? Okay. Say last try for real. Last try. It crashed while loading. Please fix. Okay. Okay, fix that line. Is it... Wait, fix the code for me. Thanks. There we go. I don't want to edit code. You can edit the code for me. Like, why do I need to edit it? If you tell me where the error's at and you know exactly where it's at, go fix it. Don't you tell me to fix a code. Okay, can we get our pixel attack game? Those are all the same. Doesn't know to edit the one spot. I'm around on my ChatGPT again today. You bet ChatGPT can make mistakes. You got short memory right there. Okay, we're almost done. Okay, that's got it. Here we go. Did we get it? Come on. Oh my gosh. Well, it's... Ah! Oh, that's so cool. Oh my gosh. I got the fall. I gotta try one more time. We're so close. That was so cool. Tons of green dots suddenly spawned and the game ended. It also spammed this in the console. Fix it. Bam. Is it doing it? No. All right, fix the code on the right. Let me grab a snack. Is it? Forget? Oh, still fixing it. Oh, we only have like 4 minutes. I'm going to run to class. We can do that, Sophia. We can probably do it tomorrow. I can find it for you. We only have... That's why I was kind of having a little bit of fun here with coding. I'll find you the video of it real quick. Whoa. Oh, it's doing it again. It just, like, destroys you. Alright. Let me go find that. Software analysis. I lost everybody. I'm sorry. Software analysis. Do I know? Salaries of a random. We might have to. Oh, wait. We might have to do it tomorrow, Sophia. But we will. Oh, wait. Long hair Brian to the rescue. Software analysis. It says it's in this one. I don't see it here, though. Do any of these look correct to you, Sophia? Like, none of these say software analysis on them, and I have 3 minutes to get to class. So we're going to head off, but if that doesn't have it, we will find it next time here on Stat 201. Bye!